This is today's contents, and today I'm going to talk about the chemical propulsion. And first, I'm going to start from the quick overview of the chemical propulsion, what kind of propulsion system exists, and what are the features of those propulsion system. And the second topic is a rocket nozzle. So any chemical propulsion system needs this device, and this is a energy conversion device from the thermal energy to the kinetic energy, and very important part for the rocket nozzle. So before I introduce several actual thrusters propulsion system, I'm going to talk about this rocket nozzle. And after that, I'm going to talk about the solid motor and bi-propellant thruster and mono-propellant thrusters. And especially here for topic bi-propellant thruster, there are two types of thrusters. One is for launch vehicle, and another one is in space usage, it means satellite usage. Okay, so let's go to the overview. So first, as I said, chemical propulsion, its principle is first, we have a chemical energy. And by some kind of chemical reaction, we convert this energy to the thermal energy. And after that, by using rocket nozzle, we convert this to the kinetic energy. So any kind of propulsion system, its final purpose is a kinetic energy. And the chemical propulsion system, it starts from the chemical energy, but at the middle, it includes a thermal energy. So these two steps are very fundamentals of chemical propulsion. And first, I want to talk about this rocket nozzle. And after that, I want to talk about the chemical reaction process. How do we get energy from chemical materials? And here, this is an overview or concept of a chemical propulsion system. So for some kind of chemical reaction, usually we need two types of materials, oxidizer and fuels. Some chemical propulsion system does need only one type of material, only fuel, but typically this is oxidizer and fuel. And by using these kind of chemical materials, we generate here combustion or chemical reaction, and we extract thermal energy from the chemical materials. And this thermal energy is converted to the kinetic energy through rocket nozzle. So this is a very basic overview of the chemical propulsion. And this chemical propulsion system includes a lot of elements. So for example, what kind of propellant do we use? Oxygen, nitrogen, hydrogen, a lot of candidates exist. And also property of these propellants. I mean here property cryogenic or storable in room temperature or toxic or green. Green is a non-toxic. And also other feature is a phase, solid phase, liquid phase, gas phase at the storage inside the tank. And also as to the chemical reaction, the most typical one would be a combustion. However, some are using exothermic decomposition for others. And also pressure feeding methods. There are a lot of methods. As to this, later I will talk more detail. And also cooling method. Today, I have I don't have enough time to explain this cooling method, but for chemical propulsion, we treat very high temperature gas, and this cooling method also becomes very important. And finally, usage for what? Launch, or upper stage, apogee kick, orbit insertion, or satellite attitude control. So depending on the usage purpose, there are a lot of types of thrusters. So in this slide, I categorized a lot of chemical propulsion systems into some categories. So in this diagram, I used two basic axes. First one is the propellant phase inside the tank, solid, liquid, or gas. And another vertical axis is a chemical reaction. What kind of chemical reaction? Combustion or decomposition or no reaction. So you see there are a lot of types of propulsion system. And also inside these tables, for example, here bi-propellant thruster, this means that it uses two types of propellant, the fuel and oxidizer. And here you see the mono-propellant thruster. This is only use one type of propellant, usually it's fuel. And also these blue rectangular means usage, launch purpose or in-space usage purpose. And this green is the propellant feeding method, turbopump or blowdown or the regulator. And also these orange rectangle means property of the propellant, storable propellant or cryogenic propellant or compressed gas. So depending on the purpose, we have to use different type propulsion system. And in this today's my talk, I want to focus on these categories. So first one is the solid motor. So propellant phase is solid inside the tank. And next is the bi-propellant thrusters. This comes here, around here. So liquid phase and combustion usage. And one usage is a launch and one usage is in space. And the final thruster is a mono-propellant thruster. This is mainly used for in-space. So I talk about those kind of things. Okay, so let's start from the rocket nozzle. So first we have to understand what kind of chemical reaction is required for our purpose. So this is a rocket nozzle, very simplified rocket nozzle model. It's called as a 1D model. So rocket nozzle is a kind of tube with changing cross section, AX. And the flow is coming from the left-hand side. And that flow has a property of density, pressure, temperature, and velocity. And the right-hand side is here is an exit. And here flow has a different density, pressure, temperature, and velocity. And in this 1D model, these density and the pressure and the velocity and the temperature are changing along the x-axis. In this here along this axis. So this is very basic and a very simple model of the rocket nozzle. But by using this nozzle, we can understand the basic characteristics of gas flow. And in this slide, I summarize several assumptions in this model. So if you are interested in the detail of this model, please check these kind of assumptions. So by using this model, we have two kinds of thrust. So first one is a momentum thrust. It is what I explained in my first talk. So it is a reaction of the ejected mass. So from right-hand side, from exit, we are ejecting the gas with a velocity VE. So as a reaction force of this VE, we get this kind of force. So this is as I explained before. And the next one is the first one. I mean, in the previous talk, I didn't talk. This is called as a pressure thrust. So in the case of chemical propulsion, usually around the exit here, the ejected gas has its pressure. And that pressure is different from the ambient pressure. Ambient pressure means like here. And when you think about this kind of the test volume, all of the parts, all the surface get pressure from the ambient. However, only this surface, exit plane, exit surface, pressure is different. It's a PE. And this pressure difference generates thrust. So this is thrust called as pressure thrust, and it's expressed by this equation. So when we think about a chemical propulsion, basically we have to consider these two effects, momentum thrust and pressure thrust. But as explained before in the previous talk, this kind of complicated thrust component is not useful to handle it. So basically we are introducing the concept of effective exhaust velocity. So that definition is like here. So simply dividing the force by m dot. M dot means the total mass flow rate from the propulsion system. And also, sometimes instead of exhaust velocity, effective exhaust velocity, sometimes we use another index, ISP, specific impulse. The difference between those are just the distance of this G, the constant. And in SI unit, it's 9.8 meter per square second. So in the point of number, effective exhaust velocity and ISP is just 10 times the difference, almost 10 times the difference. So by either way, you can express this effective exhaust velocity. So sometimes I use exhaust velocity and sometimes I use ISP. And the unit of ISP becomes a second. It's a little bit tricky, but it's a custom. Okay, so based on the previous model, we have to use 4 governing equations. In this talk, I wanna say about explain the details of these equations, but the concept is very simple. So first one is the mass conservation, and the second one is the momentum conservation, and the third one is the energy conservation, and the fourth one is the equation of state. So the concept itself is very simple. So by using these 4 equations, we can derive a lot of important information. But inside today's talk, I will skip detailed derivation of the equation from those governing equations. And also in this slide, I want to introduce one more important concept. It's a Mach number. So it's a ratio of flow velocity and local speed of sound, local sound speed. It would be the most important non-dimensional number in compressive flow. And this M frequently appear in my talk. Okay, so this is one equation derived from the 4 basic equations. This equation expresses a relation between velocity, flow velocity, and cross-sectional area of the nozzle. And here you see the Mach number. And this equation means that M is larger than 1 or smaller than 1. By this, flow characteristics is changed very much. So in the case of the flow velocity is less than sonic velocity, so this is how to say standard case. In this case, you see dVdA becomes negative, and this means when you increase the area, velocity will be decreased. So in this kind of divergent tube, flow will be decelerated. And in the case of the converging tube, this means that dA is decreasing. Then it means velocity is increasing. So by using this kind of converging tube, we can accelerate the flow. So this is a basic feature. However, when Mach number exceeds 1, this characteristics is changed completely. So when you increase the area, velocity is increased, and when you decrease the area, velocity is also decreased. So to accelerate flow from the static state to the very, very high speed, exceeding the sonic speed, we need to start from here, and we have to go to this region. And also from this equation, another important point is M is equal to 1 can be achieved only in this case, left-hand side case. So from this equation, if you substitute M equal 1, you will find that dA should be 0. This means straight tube area. And the straight tube area can be attained by 2 configurations, left and right. But in the case of the right case, if flow coming from the left with M is less than 1, it will be decelerated. Then velocity is slower, becomes slower. Then m is not reaching to the 1. And in the case of m higher 1 flow, in this case, diverging tube will accelerate the gas. So very high flow is accelerated more and more. So Mach number will not reach to the 1. So by using this tube, we cannot attain the Mach number 1. So Mach number 1 only can be attained only by this configuration. And this configuration is called as a rocket nozzle or lava nozzle. And by using this configuration, we accelerated gas up to here from Mach number 1, and in this region, exceeding Mach number 1. And also, this feature tells us very important and interesting feature of the flow. So, for example, if you change the exit state, in this case, in this example, if you change the exit area of the nozzle like this, here, this area, this it's called a throat. Throat Mach number is always 1. So even if you change the downstream condition like this, upstream condition will not change because here at throat, m is equal to 1 and the same, so same property. So for the upstream part will not change. So this means if you get supersonic flow, mass flow rate and flow condition, upstream flow condition is determined only by upstream conditions. So if you change downstream condition much, it does not affect the upstream condition. So this means mass flow rate is determined only by upstream conditions by this equation. And also from the governing equation I showed at the beginning, by reforming those equations, we can derive this kind of exit velocity expressions. So this is a most important parameter. It's related to the moment of thrust. And you see here inside this pressure ratio. And this pressure ratio is determined by the next equation. So by solving the next equation, you can obtain the pressure ratio and substituting it to into the above equation, you will get this exit velocity. And by using this exit velocity, you can obtain this kind of thrust expression. So actual expression of the thrust is somehow complicated, but all of these complicated parts is included into this coefficient CF. It's called as thrust coefficient. And we can get this kind of simple form. So thrust is equal to AT. AT means the area of throat times P0. P0 means the upstream pressure and thrust coefficient. And this thrust coefficient is determined by the type of gas, gamma, and the pressure ratio and aperture ratio. But as I said in the previous slide, this pressure ratio is determined by aperture ratio. So this means basically this CF is determined only by aperture ratio and also gas type. So when you design a rocket nozzle, you have to take care about this value. But only this value should be taken care of. So this is thrust coefficient. So this slide shows how thrust coefficient is changing by multiple parameters. So here I change the pressure ratio. So pressure ratio, this pressure ratio is a combustion chamber pressure divided by ambient pressure. So in the case of a large ratio, in this case 10,000, this blue line. So basically, if you increase aperture ratio, this CF is increasing. This is a case of the in-space usage. I mean, in-space usage, ambient is basically vacuum. So this ratio becomes almost infinite. So this is a vacuum case. But if you use a propulsion system for the launch vehicle, first, at the initial point of the launch, there is an ambient pressure around the rocket. So this pressure ratio becomes finite value, like 10 or 50 or 100. So for example, if you have a P0 5 megapascal and ambient pressure is 1 atmosphere, so 0.1 megapascal. In this case, pressure ratio becomes 50 and CF becomes this green line. And we will find it has an optimum maximum value. So according to the ambient pressure, we have to select this kind of nozzle condition or aperture ratio. But very difficult point for the launch vehicle is ambient condition is changing when you launch the rocket from the ground to the space. So this graph shows how the pressure is changing by the altitude. So altitude 0, so we are here. But when you launch the vehicle, if it reaches to the 50 kilometers, ambient pressure becomes almost 1% of the atmosphere. So cannot change. So you have to design your rocket nozzle by considering this kind of ambient pressure change. And also one idea to adapt this kind of condition is a change of the nozzle shape. So actually some rockets utilize this kind of idea. Actually, this is Ariane 5 rocket engine, Vulcan 2, and it has an extension nozzle. So this part can be extended. So altitude becomes high, it can extend the nozzle skirt, then it can increase the aperture ratio. Okay, let's return to the thrust expression. So this is another form of the chemical propulsion thrust. So in this expression, we are using the m dot. This is a mass flow rate, and c star. It's characteristic velocity, and it's called as c star, and again cf. So by using this form, we can keep the mass flow rate constant, and we can see the effect of the c star or temperature of the combustion chamber. So this c star, it's inside. It consists of a combustion temperature and the specific heat and expression, and also this gas constant. So basically, this characteristic velocity c star expresses the status of the combustion chamber. And if you increase this c star, you can increase the effective exhaust velocity. So there is this kind of relation. So if you want to increase specific impulse or exhaust velocity, you should increase this c star, and it means you have to increase temperature. So this slide shows this its dependence. So temperature versus c star. So you see it's simply increasing, and also one more remarkable point is molecular mass. So our gas constants in the previous slide, this gas constant, it's not a universal gas constant. So, and it's like this. So here, molecular mass is related. So if you use a lighter molecular mass gas, this c star is increased like this. So this is the main reason why we want to use lighter molecular weight gas for our rocket propulsion system. Okay, so the final part of this chapter, let me talk about the 2D effect a little bit. So far my talk is according to the 1D model, but actual thruster, actual nozzle has a 2D configuration or 3D configuration, and there are such kind of effect. So in this slide, if flow and exit pressure is equal to the ambient pressure, in this case, flow will be smoothly connected to the ambient gas. as shown in this slide. However, in actual cases, many cases differ from that. So first one here, this is under expansion case. This under expansion means expansion is not enough and gas pressure is still high here compared with ambient pressure. So it's called as under expansion. And in the case of over expansion, this is too much expansion. Then pressure is too low compared with ambient. So in this case, this exit pressure is lower than the ambient. And what happens for these two cases? So flow is coming like this, In the case of under expansion, this region has higher pressure than ambient. Then this flow tends to expand surroundings, like as shown by these arrows. And in this case, it's not a so big problem. But the problem is a second case, overexpansion case. In this case, here, pressure is lower than the ambient. And ambient gas tend to come into this area like this. And if this pressure difference is so large, what happens is here. So due to the effect of the incoming flow from the surroundings, flow is separated from the nozzle surface like this. It's called as a flow separation. And by this, our 1D model, its prediction becomes much different from the actual this kind of flow separation flow. So if this happens, we cannot, it's very difficult to correctly predict the nozzle flow. So basically we want to avoid this kind of flow separation. And also this flow separation means actual nozzle cross section becomes like this. So in the case of this example, from this point, from the separation point, nozzle area becomes lower. So this means here, basically, Mach number is higher than 1, and this means a deceleration. So accelerated gas is decelerated from this point again. So it's not happy for us for the propulsion. So we want to avoid this kind of status. So for that, we have this kind of figures. So this is the same as a previous one. Basically, horizontal axis is aperture ratio, and vertical is a thrust coefficient. And there are some kind of optimal values. And here, what I want you focus is this area. So this red area is flow separation will occur definitely. So we have to avoid this area. And this orange region, this region would be like a, maybe flow separation will occur. So we want, if possible, we want to avoid this area. So around here, flow separation will not occur, so it's okay. But the orange area, if possible, we should avoid, and the red area we have to avoid. So by using this kind of diagram, we have to design the nozzle configuration. Okay, so this slide summarizes my talk about chapter 2 about the rocket nozzle. So I think the most important relation is this simple relation. So thrust has two kinds of expressions, ATP0 CF or m dot c star CF. And from these equations, we can know that if you want high thrust, the methods are large throat, this means this throat area, or high combustion pressure, or high flow rate. And if you want high effective exhaust velocity or high ISP, what you should do is high combustion temperature or low molecular mass propellant from the C-star dependence. And also as to nozzle shape, it's related to the by this thrust coefficient. In the case of vacuum, it's very simple. High aperture ratio is best. So as big as possible, you can design the nozzle. And in the case of in air, the physics is a little bit difficult. So there is a first optimum aperture ratio, and also there is a flow separation. So we have to take into account these two effects into our nozzle design. Okay, then I wanna move to the chapter 3, solid motor. So this slide shows a concept of solid motor. I think the good point of solid motor is its simplicity. So basically, it consists of a solid propellant. It's a kind of slowly combusting explosive. Or in other words, it's a gunpowder. So it includes oxidizer and fuel. And by itself, it can combust. So this is solid propellant and combustion chamber. And basically, these two, solid propellant and combustion chamber is in the same room. And after that, we have a rocket nozzle here. And to ignite the solid propellant, we need a certain kind of igniter. So it's very simple concept. So in this slide, I'll show you one typical example of the solid propellant. It's called as a composite propellant. Oxidizer is ammonium perchlorate. Sometimes it's abbreviated as AP. And fuel is many types of fuels, polymer, binder, and PVC and HDPE. So a lot of kind of polymers can be used as a fuel of the solid propellant. And also some metals like aluminum can be used as a fuel of the solid propellant. So this is a composite propellant and actual appearance. And it's a kind of a soft gray. So by applying your force, somehow you can deform this propellant. And in this slide, I want to talk about the basic mechanism of the combustion of the solid propellant. So solid propellant, in this figure, this purple block shows a solid propellant. And the solid propellant itself, basically, it does not combust. For the combustion, first, it needs to be decomposed and vaporized and becoming gas. So by inputting heat from somewhere, we can decompose, melting, decomposing, or vaporizing this solid block. And we can generate gas like this to right-hand side. And this gas react each other and generate heat. So in this figure, this is a heat generation zone. And this combustion heat is going back to the surface. Then it melts, decomposes, vaporizes the solid propellant, and feeds the reactive gas to the combustion area. So this is a basic cycle of the combustion of solid motor. And this feedback system determines the m dot, mass flow rate from the solid propellant. So reactive gas. This is actual gas fed from the solid propellant. So this feedback determines the mass flow rate. And also in combustion chamber, this reactive gas was an inlet for the combustion chamber, but exit is a nozzle. So we have to take account those balance. So as I explained before, we have this kind of relation for the mass flow rate. So I showed this kind of relation. And from this equation, you can derive this kind of equation to mass flow rate. And this is an exit condition. And inlet and exit should be balanced. So we have to satisfy this equation. And from this equation, pressure inside the combustion chamber is determined. So here PC is described like this. So here you see rho V is the solid propellant density, and C star is C star I explained, and AB is the area of the burning point, and AT is the throat area. And final one, this R is a burning rate. It's a velocity of the burning. So burning surface is proceed to the upstream, and its speed is expressed by this rate. And this is very important parameter for solid propellant. But to know how it's determined is not so easy. Actually, we don't have any kind of analytical expression for that. Instead, we have an empirical expression for that. That is this. It's sometimes called as a Wheeler's burning law. And it's related to the combustion pressure, combustion chamber pressure. So from this slide, I explained the heat feedback is very important for the solid propellant combustion. And from this slide, I think you can immediately understand pressure is very important. So heat transfer from this combustion area is conducted by radiation and also convection. And for convection, pressure plays a very essential role. So combustion area, its pressure is very important, and it's strongly related to the burning rate. So this is appearing here. But its actual dependence is very difficult. So we are introducing two adjusting parameter, pressure exponent and coefficient here. Actually, when you see some solid propellant properties, you will find these parameters. So this is pressure exponent. And basically, this pressure exponent ranges from 0.2 or 3 to 0.5 or 6. Always, it's less than 1. This is for the stable combustion of the stable combustion. If it exceeds 1, combustion will be extinguished or exploded. So for the stable combustion, this pressure component should be less than 1. And typically, around this value is selected. And also another important factor of the combustion and which determines the pressure is this one. So area of burning. So it can be controlled somehow by the initial ignition part and the shape of the solid propellant. So first example, in this case, burning area is like this, and this burning area will going to like this. So very simple burning. In this case, we can get very standard combustion. But the disadvantage of this combustion method is thrust is not so high. It means combustion area is not so large. So only the bottom surface of the cylinder is combusted. So in this case, the feature of this combustion is a low thrust, but quite constant pressure we can obtain. And another method is inside combustion, as shown in this bottom here too. So in this case, when combustion proceeds, combustion area, combustion surface, its diameter is increasing, and it means combustion area is increasing. So this results in this kind of increasing pressure. And this is quite bad for propulsion, especially for launch vehicle, because launch vehicle is losing its weight by combustion. So combining with this solid propellant, pressure is increasing and weight of the rocket is decreasing. And this means the acceleration is increasing very much. So this is not so preferred. And another candidate would be like this. So outside combustion. Maybe by using this kind of configuration, we can start from the very high large area and it's gradually decreasing. So this would be good in the point of thrust and acceleration. So surface area is enough large and acceleration would be constant. So weight loss effect and decreasing surface area will be compensated, and maybe constant acceleration will be attained. So in this point, it's good. But disadvantage is clearly structurally it would be weak. So it's a kind of a candy stick. So it's very difficult to keep this shape with strong vibration. So actual solid propellant motor or actual rocket utilizing this kind of inner combustion. So in this case, star-shaped hole is set inside the solid propellant, and it will be combusted, and maybe combustion surface will become like this. This is just my drawing, but roughly this kind of combustion will occur. So at the beginning of the combustion, mean diameter is small. However, shape is complicated, so fineness. So regardless the very small average diameter, surface area, surface has so large. And as a last status, mean diameter becomes large. However, fineness of the surface is reduced. So as a result, by using this kind of shape, we can realize almost constant pressure. Of course, we need a fine tuning of the shape, but this kind of idea work for actual solid motors. So this is one example of the actual solid motor, solid propellant motor. So here you see a lot of configurations. But here you find that 8-point star internal burning ring cavity. And this fin shows fin of the star, one fin. So basically, most of solid propellant motors employ this kind of settings. Okay, so next topic is a bi-propellant thruster. Time is consuming. So bi-propellant thruster for the launch. So first for the launch. So this is a concept of a bi-propellant thruster. We need oxidizer and fuel. And we have to mix those and combust. But first, I wanna focus on this part, feeding part. So in this figure, I just inject oxidizer into this, but actually it's not so easy like this figure. So combustion chamber, its typical pressure is at 10 megapascal, very high pressure. And injecting liquid into this high pressure region, we need much higher pressure here and here. And the point is how we prepare or how we make these higher pressure than combustion chamber. One method is very simple one. So let's enclose a high pressure gas inside the tank. It's called as a blowdown method. So there are two tanks, and here upper part is a gas, high pressure gas. And this high pressure gas will push this liquid to the downward, and it feeds the liquid into the combustion chamber. It works so. However, there are some disadvantages. So first one is pressure is changing. Here, liquid is the amount of liquid is decreasing and the gas is expanding, then pressure is decreased. And this means flow rate changes and reaction changes and thrust changes. In the point of usage, it's not so good. And also, second one would be more important. So we need a very strong tank enduring the high pressure. So we have to prepare a very big high pressure tank, and it becomes very heavy tank. And especially for launch vehicle, it is very bad. And the second method is almost similar to the blowdown method, but it's called as a regulator. So by using the regulator, pressure regulator here, we can keep the pressure constant downstream area of the pressure regulator. So by using this device, we can get a constant thrust. So in the point of operation, it would be nice. And also here, high pressure gas, very high pressure gas is only here. So this is gas source, and the gas is coming like this, and the liquid is going like this. So somehow lightweight tank can be used here and here for fuel and oxidizer. However, chamber pressure should be lower than this oxidizer tank and fuel tank pressure, and these tank pressures should be much larger, much smaller than gas tank pressure. So this means by using this regulator method, it works, but we cannot get high combustion pressure at this area. If we want high pressure here, we need higher pressure fuel and oxidizer tank, and also we need much higher pressure gas tank. So this means very heavyweight systems. So method is turbo pump system. So it uses a pump. So this is a pump part. This pump will increase the pressure like this, and this pump is driven by the turbine here. So then it's called as a turbo pump. And by using this kind of turbo pump, we can get very high pressure. And also we can get low tank pressure, and it means a lightweight tank. So it's very nice for launch vehicle. However, drawback is here. This system is very, very technically difficult. So I think most of the difficulty of the rocket launch vehicle is here. So turbo pump and its surrounding systems. So this is a very difficult system, but it's very effective. Yeah. So this slide is some kind of a summary. I mean, so for orbital launch, we need a high delta V because of orbital velocity and some kind of loss. And also against the Earth's gravity, we need a high thrust. And high delta V, we need a high exhaust velocity and a low structural coefficient. And also for high thrust, we need high combustion pressure. And this result in turbo pump system. We have to select for orbital launch system. So actual bi-propellant thruster for orbital launch is like this. So here we have a turbo pump system. And this slide shows a typical propellant for launch vehicles. There are I think most typical oxidizer would be oxygen, and especially to compress this oxygen to very small volume, we use liquid oxygen, and this means we need a very low temperature, like 90 Kelvin. So this kind of system is called as a cryogenic system. And also there are two typical fuels. First one is hydrogen, and the second one is hydrocarbon-based fuel. The hydrogen, its remarkable feature is a molecular mass, very lightweight, and it results in very high specific impulse, high exhaust velocity. So in the point of performance, it's very nice. However, to compress this into small space, we need very, very low temperature, like a 20 Kelvin. And it's much lower than this 90 Kelvin. And it's very difficult. And in the case of a hydrocarbon-based fuel, molecular mass is higher than hydrogen. Then in the point of performance, it's worse than hydrogen. However, its storage is very easy. So usually inside a room temperature, we can store this. So it's very easy handling. And by using these fuel and oxidizer, next point is how we drive the turbo pump. So how we generate a high pressure, high temperature gas to drive turbine. And there are two popular methods. First one is a burner, and another one is to use regenerative cooling. And also another categorization is used gas treatment of the used gas in the turbine. So after turbine, that gas is dumped or reused. In the case of dumping, it's called as open cycle. And in the case of reuse, it's called as closed cycle. And by these two axes, we can categorize turbo pump system into 4 systems: gas generator, stage conversion, and expander bleed, and full expander. So by selecting which system, performance of the total propulsion system will change. So here I want to explain these turbo pump systems, cycles, engine cycles. So first one is a gas generator cycle. This might be a quite a simple one. So here you have a fuel and oxidizer. So above this slide, let's imagine the fuel and oxidizer tank, and fuel and oxidizer are coming this, and this P means a pump, and this T means a turbine, and it's connected by shaft. So this concept is very simple. So tiny amount of fuel and oxidizer are extracted from the pump, and they are combusted inside the gas generator. And this gas is used to drive turbine here and here. And after that, this gas is dumped like this. So in this case, system is quite simple. However, this gas in this slide, M2 dot, this gas cannot be used as a rocket propulsion system. So this becomes a loss. So actually, effective exhaust velocity will be decreased by this factor. And the second system is, okay, so let's not to dump the gas, and let's use all of the gas. So in this system, here, pre-combustor exists here, and after turbine, they are sent to this combustion chamber. This system is very nice in the point of performance. So we can get very high thrust, and also we can get high specific impulse. It's very nice. However, the system becomes very difficult. I mean, for example, this is 10 megapascal, for example. So here maybe 12, and for here before turbine maybe 18. So pre-combustor would be 20 megapascal or something like that. So we need very high pressure pre-combustors. So all of the elements becomes very high pressure. So technically it becomes very difficult. But in the point of performance, it's very nice. And another concept is here, expander system. This is quite unique, I think. So this does not use pre-combustor. This just use here, cooling of the surface of the combustion chamber and nozzle. So to protect these metal parts, basically we need some kind of cooling system for this kind of propulsion system. And for that, we can use fuel or oxidizer. In this example, I'm using the fuel. So by using fuel, we can cool down the surface to protect the surface itself. But this cooling is heating up from the side of the propellant fuel. So during this cooling process, the fuel is its temperature is increased. So here you get high temperature fuel, and by using this high temperature fuel, you can rotate drive turbines. So this is a concept. However, by using this method, there is a limit for the heating, and it means a limit of thrust. So it's a very simple system, and all of the gas can be used. So it's very high performance. However, there is a limitation for the thrust. So typically, it can be used for the second stage or something like that. So this is an open system of the expander. Sometimes it's called as an expander breathe cycle. So here you see bypass line from here. So by using this bypass line, you can somehow decrease the limitation of the thrust. So in this case, the skin pulse is decreased a little bit, but you can increase the thrust. Actually, in Japan, we are now developing the next generation launch vehicle. It's called as a H3, and H3's first stage will employ this expander breathe cycle. So for first stage, we need a high thrust, but we want a simple and reliable system. So they selected this engine cycle. Okay, so this slide shows a summary of the features of open and each the 4 engine cycles: gas generator, stage of combustion, expander breathe, and free expander. In the point of performance, stage of combustion is fantastic, but very difficult and somehow low, high weight, and maybe cost is very high. So recent trend would be gas generator. Performance is lower than the stage of combustion, but development cost as a system, total balance would be nice for this gas generator. Okay, so here I show some example of the engines, but I skip. Okay, for that.
No problem. We had some issues at the beginning, so we can overlap with it.
So I have still 2 chapters. Yeah, it's very difficult to manage that time. Okay, so next is a bi-propellant thrusters for in-space usage. So in the case of in-space usage, for the satellite usage, typically this kind of system is used. So instead of a power pump, we are using a pressure regulator or blowdown system. So in the case of in space, very high thrust is not required. So combustion chamber pressure, we can decrease combustion chamber pressure. So this pressure regulator system works so. Okay, so let's see the actual performances of this bi-propellant thruster. So typically its thrust ranges from 100 Newton to 100 kilonewton, and exhaust velocity would be around 3 kilometers per second. By specific impulse, it's around 300 seconds. And the main purpose is basically main engine for satellite and space probe. And as a fuel, typically hydrogen is selected, or hydrogen-based other fuels like MMH and UDMH, monomethyl hydrogen or unsymmetrical dimethyl hydrogen. But all are hydrogen-based fuels. And as to oxidizer, NTO, nitrogen teroxide, commonly used. And monthly, it's basically it's a NTO, same as NTO, but slight amount of additives of nitric oxide. So these are typical oxidizer and fuels. And for example, this is an application example. So this is a Japanese ISS transporter, HTV. And here you see a thruster. This is the bi-propellant thruster. And these specifications of these thrusters. So there are 2 types of thrusters. So here you see 4 big ones. These are R4D by Aerojet. It generates almost 500 Newton thrust and over 3 kilometers per second exhaust velocity. Nice performance. And the fuel is MMH and the oxidizer is MON3. And the small thruster here is a R1E. In the case of a small thruster, thrust is of course lower, and the specific impulse is also a little bit decreased. But in this system, what I want to emphasize is not these performances, the number of thrusters. So big thruster, the whole, but small thrusters, it's not appearing in this figure, but in total, it has 28 thrusters for one satellite, one module. A lot of thrusters. And associated with these thrusters, we need valves, pipes, and tanks, and we need a lot of things. Actually, let's see the inside. So this is a diagram of the system. So here, high thrusters, and here in this diagram, just only 4, but actually these are in total 28 thrusters. So total system is quite complicated. Sorry, this is Japanese version, so I prepared the English version here. And you see, so my first impression of this diagram is so complicated, and who is developing this kind of complicated system? But each element of this system is, of course, necessary. So if you have a time, please check each element. What is this purpose and what is this purpose? It becomes very good line. But here, I briefly explained the system, so very briefly. So upper part is all of pressurization system. So this system is using a blowdown system. And here, around here, oxidizer system and fuel system. And in this area, thrusters. So this diagram is very nice. So they are using 3 colors, blue, green, red. So we can easily understand the status. But usually system diagram is like this. So this is another case. This is a Galileo Space Probe, very famous Jupiter probe. And in this case, it's like this. So complicated, but yeah, all of the elements are necessary. So by using this slide, what I want to say is when you develop a bi-propellant thruster, of course, thruster itself is very important. So fuel, oxidizer, when you see the thruster, injection method, combustion efficiency, combustion oscillation, and cooling, nozzle insulation, a lot of elements. And these are very important. However, this kind of system and how you develop this system is also very important, which determines the total system performance of the propulsion system, especially reliability, performance, those kind of things. So, for example, if you have a chance to develop a new satellite and where you have a chance to develop a new propulsion system, I think what you have to do is a right-hand side. You have to design all of the system. So selecting the thruster, selecting the valve, and selecting the tank, and how to combine those things. These are quite complicated, but very important. And depending by that, the total performance would be determined. So finally, final chapter. So monopropellant thruster. So in the case of mono-propellant thruster, as its name shows, it only uses only one propellant. Usually it's called as a fuel. But instead of that, we are using a catalyst bed. So in this thruster, instead of combustion, we are using the decomposition, and especially exothermic decomposition. Then we get heat. And also, in the case of monopropellant thruster, we are removing one tank, and it means the system becomes simpler. So to enhance that feature, sometimes blowdown system is preferred for this thruster. By using this blowdown system, total system becomes more simpler. Okay, so let's see some example. So in the case of monopropellant thruster, it's not a combustion, decomposition. So due to that, thrust level is somewhat lower than bi-propellant thruster. So typically from 1 Newton to 1 kilonewton. And also effective exhaust velocity is lower, around 2 kilometers per second. This is due to smaller heat generated by decomposition compared with combustion. So this monopropellant thruster is typically used for RCS, reaction control system. So for reaction control system, we need a lot of thruster heads. And to prepare a lot of thruster heads, the simplicity of monopropellant thruster is very nice. So yeah, typical usage is this RCS. And the fuel is typically hydrazine, and the catalyst, this is very important. very widely used catalyst is called S405. Former it's called as a Shell 405. It's a granular aluminum coated with iridium. So aluminum particles with coating of iridium. And this is one example of the thruster. So the thrust is about 20 Newton, and the thrust is about 2 kilometers per second. So in the point of performance, it's lower, but simpler system we can realize. So this is an example of the diagram. Again, you may think this is also complicated, but I think somehow simpler than previous one. So here, fuel part, oxidizer part, and pressurization part. And right-hand side, these many thrusters are all mono-propellant thrusters, and only fuels are required for these thrusters. So compared with the previous diagram. And then finally, I want to talk about the next trend of mono-propellant thrusters. So here you see satellite and two guides. And do you think they are astronaut? You're right. So they are actually handling the hydrogen. So to handle hydrogen, we need this kind of protector usually. So this means hydrogen and also MTO has quite toxic features. So to express toxicity of the material, there are a lot of methods. So here I employed three methods. First one is a GHS spectrogram. And so according to GHS spectrogram, we had a lot of signs, flammable and corrosive, toxic, and a lot. Another index is a NFPA. This is a USA index, and there are three indicators: health, flammability, and reactivity for all. And the maximum is 4, so almost maximum score. So great. And also another index is LD50. This is a lethal dose. So yeah, detailed description. Yeah. So definition is like this. So yeah, this means a fatal amount of the material. So if this number is lower, it means very dangerous. So in this case, 60 milligram per 1 kilogram. So quite dangerous material. And also for MTO, these signs are like this. So anyway, these are toxic. Of course, by using this kind of setup equipment, we can handle it. And we have handled these very nice propellant. However, if possible, we want to avoid these kind of handlings. So especially in the point of cost and period. So then recently, there is a movement to reduce the toxicity of mono-propellant thrusters and to change the propellant from very toxic one to the friendly one. And we use the expression green, more friendly propellant. And those examples are these. And finally, I will briefly show these examples. So first one is called Han-based green propellant. Han is this kind of material. It's a salt, a kind of salt. And yeah, its melting point is 48. So it in room temperature, it's a solid state. But it is a salt, and it can be easily solved into water. So very high solubility. So when we use this Han for the monopropellant thruster, we will use this kind of solution. So this is one example, AFM 315E. This was developed by Aerojet. And in this case, density is 1.5 and not freezing, no freezing. So it's very nice for as propellant. And also, yeah, remarkably, yeah, you see GHS spectrogram. There is only 4 signs, and also, yeah, LD50 is 10 times higher. This means much safer. So in this point, this hand-based propellant is somehow safer than previous hydros. Still, we need to care for the treatment, but better. And in the point of performance, here you find that specific impulse is higher than previous one. So in this point, it's nice, yeah, higher performance we can get. And also another candidate is called as ADN-based green propellant. It's again, it's a salt, a kind of salt, and the melting point is like this, so it's a solid status salt. And by solving it into the methanol or water, we use it as a mono-propellant. And one typical propellant is called as LMP 103S. And again, yeah, you see, pictogram is decreased down to 2 max, and LD50 is also over 700, so safer. And also, yeah, you see again higher specific impulse. And these two propellants have been already used in space. So in the case of hand-based propellant, satellite named as a GIMP, demonstrated its usage in space, and also in the case of this ADN-based propellant, PRISM satellite used it. So gradually, these green propellant becomes a mainstream of the monopropellant, but still hydrazine is mainstream. Okay, so I talked all of the material I prepared. So I talked about this part of the thruster, but here, this time I talked only this part. So hybrid rocket and cold gas thruster, those are, yeah, I have no time to talk. So if you are interested in those, please check my materials. Okay. Thank you for hearing. This brings the end of my talk. Thank you.
Thank you. Thank you, Professor. I don't know if there's any questions first here in the room.
I have a question out of curiosity.
Yeah. Okay, so it was just a question out of curiosity. I really have no background in propulsion, but yeah, I've heard about the aerospike puzzles, and it seems to me that it's exactly what you said is bad. So why do they exist?
Aerospike?
Yeah.
So here I cannot show, but yeah, it's a kind of how to say altitude compensation nozzle. Okay. It can adjust the nozzle area according to the ambient pressure.
Okay.
So its main merit is that. So it's similar with this tension nozzle. So due to its unique shape of the nozzle, its expansion area is adjusted according to.
It's not inverted, or it's inverted, right?
Yeah, inverted shape.
Okay.
And
this
main
doesn't. Is it a problem?
Yes, main problem is cooling, I think.
Okay.
So it's inverted shape, and access to that inverted core inside the core is not easy. So all of the parts should be cooled properly for bi-propellant thruster, and it's not easy in the case of aerospike engine. So ideally, it's very nice. It can get very high performance from the ground to the orbit. So many researchers have studied it, but not yet realized as actual rocket engine.
Okay, thank you.
Well, I have a quick one regarding the state of the art. In which area do you see these days the high amount of progress being made when it comes to chemical propulsion systems?
Yeah, actually, that usage is very wide. So my first answer is it depends on what you see. So solid motor, or launch vehicle thruster, or in-space usage. So yeah, when you see a launch vehicle, I think the trend is internal performance. I mean, internal performance means cost and period and payload mass. So by seeing all of these aspects, they are trying to the best solution. And so, yeah, 20 years ago, maybe hydrogen system would be the mainstream due to its very high performance. But recently, kerosene system is sometimes used. And it's due to the not by performance, it's a total performance of the launch vehicle. And I think its trend will proceed more for the launch vehicle. And also, I'm not sure it becomes mainstream, but there is a other type of tar pump. It's called as a electrical pump. So by using battery, we can drive the pump. And actually, the company Rocket Lab has a launch vehicle named as Electron, and it employs a electrical tar pump system. So it's actually not tar pump; it's an electrical pump. Yeah. So in this case, there is a very high weight demerit, but the system becomes very, very simple. And we can avoid the development of the tar pump, and it's very nice. So maybe, and depending on the development of the electrical motor and battery, it becomes more popular, I think. And in the case of in-space usage, as I said, finally, towards a green propellant, this movement is very strong. So especially for new space field, a lot of newcomers are coming. And for those, hydrogen is very difficult to treat, actually. So more easy handling propellant is very welcome. And I think this trend is quite sure. Yeah.
Okay. Thank you.
In the propellant, the green propellant,
Yeah.
You add water just to solubilize the salt.
Yes.
But this decreases the heating power effect.
Yeah, I think so. Yeah. So, but actually, yeah, it's in room temperature. It's a solid, so we need some kind of liquid to mix it. And I don't know the exact detailed process how did they select this kind of combination. But yeah, I believe that they did a lot of tests, and as a result, it is a nice. But yeah, even water, it includes oxygen, and in a certain temperature, it can become oxidized. So
maybe I can add a little bit to that as well. I know that in some mixtures they add water because it just expands a lot when it becomes from liquid to vapor. So it creates more pressure.
Okay.
It decreases the temperature but creates more pressure. So you have more gases.
Okay.
So maybe sometimes they take this into account also. And yeah, I had a question regarding to the previous one where you said which propellants are the most used. And I think recently a lot of recent rockets that are designed use methane. So Starship, it's called the company from New Zealand, Rocket Labs, is also doing a new methane rocket. There are many companies using methane. Maybe you have a comment about this.
yeah, in the case of Starship, they are imagining some kind of, how to say, ISRU on the Mars. So actually, I'm not so familiar with the usage of methane, so I don't know so much. But yeah, also in Japan, there was a development to use natural gas for that for the propellant. But I don't know the detail. But there was some kind of difficulty for the development, and currently not so much effort for that.
Okay, thank you.
Okay, I think with that we can wrap it up. Thank you again, Koizumi. Thank you everyone for joining, and we'll see everyone on the next one, which is when exactly?
January
13th.
13. Okay. Yeah. Thank you again.
Thank you, everyone.
See ya.
Bye bye.
Thank you.